What for?
Sir, this is Chip Mayse. He's probably the only theology major we go at CQ, and he's here to give a presentation on why you should pay attention to case 57. So,
Or should have paid attention. Numerical analysis? Is there anyone here who has no idea what numerical analysis is? You have no idea. Okay, what's your background? CS, engineering, philosophy, French? What's your what? No, him. Yes, the guy who says he doesn't know what numerical methods are. Okay. Well, numerical methods is basically the methodology of doing complicated mathematics with a machine that can only add, subtract, multiply, and divide. In other words, coming up with algorithms that that combine those operations in such a way that you can simulate things like calculus and so forth. And you'll be seeing lots of that this evening because that's really what this talk is about. The motivation for it is that a few years ago, actually on January 3rd, 2005, while watching USC pulverize Oklahoma, I came up with an inspiration which helped us solve a long-standing problem, and it involved a trick that you might be able to use. You might not be working in the same application area that we are, or that I was, but the trick that we came up with should be quite generally applicable. It's simple, it's obvious, and it took me way too long to think of it. So I thought I'd come here and tell you folks about it and maybe save you a couple of decades in case you do this kind of stuff. If you're not familiar with numerical analysis, then you've probably never seen the algorithm that's known as Newton's method. But to make a long story short, it's a method of finding or approximating a solution to an equation, typically of the form f of x or f of t, some independent variable, is equal to 0. Then Newton's method iterates rapidly from an initial estimate of the x that might make that equation be true. Newton's method, or any other root finder, iterates rapidly to an approximate solution to that. And the trick is we had an intrinsically iterative problem which was ill-behaved, and we had an unsatisfactory iterative algorithm for solving it. And I had thought for some time, you ought to be able to do this with a root finder. And those are not ill-behaved for the most part. They converge rapidly and nicely. So we came up with a trick that enables one to transform a particular problem that enables one to use a root finder to approximate a solution to it. And if you don't have time to stay for the rest of the talk, you've just heard 99% of the value of it. So let's see what we can do. As the slide advertises, I'm with what's known as the Space and Geospatial Intelligence Business Unit of SAIC. We work primarily, SAIC is an employee-owned company that does contract analysis and stuff like that for the government. Our business unit works primarily for the National Reconnaissance Office, the National Geospatial Intelligence Agency, the Director of National Intelligence, and the Office of the Secretary of Defense. The group that I'm in specifically, the program that I'm in, which is called Modeling, Simulation, and Analysis, we are the proprietors of ISIS and Cosmos, which are a couple of large-scale, roughly 1 million lines of code simulators that have been around since about 1990. And they are used for analyzing the behavior of all kinds of large-scale military systems, but especially reconnaissance satellites or reconnaissance aircraft or groups of these. And what we typically do is use them to simulate the performance of a reconnaissance system, a bunch of airplanes and or a bunch of satellites, against a very large number of targets, that is, things people want to take pictures of or apply sensors to. When I use the term target, I'm not talking about shooting at it. That's other people's department. In this case, it's targets in the reconnaissance sense. So let's see if we can motivate this. In general, space-based reconnaissance assets are oversubscribed. They get all kinds of requests. There's only so many satellites. They're very expensive. They can only be operated for limited amounts of time before they have to do things like recharge their batteries and stuff like that. So each one of these things only has a certain amount of operating time each day. And there's all kinds of other constraints that keep them from being heavily available. And there's all kinds of people who want this information. People like the National Command Authority, JCS in this case is the Joint Chiefs of Staff, the intelligence agencies. Those I think you recognize. The NSA they're primarily the signals intercept intelligence people. This is the National Geospatial Intelligence Agency. These are the folks who store and archive all the imagery that comes from the imaging satellites, pictures, radar, things like that. And also the various branches of the service and operational military intelligence agencies. These people are mailing in requests for intelligence collections all the time, and it adds up to a lot more than the overhead reconnaissance assets can do, whether we're talking about aircraft, spacecraft, or you name it. So for those of you who are interested in operations research, there's a lot of interesting optimization and scheduling problems that come up because of this. In an overall general sense, we want to come up with intelligence collection schedules that are optimal in some sense. What I mean by a schedule is a plan for performing a specific set of sensing operations on a specific sequence of targets. We generally distinguish between planning and scheduling. Planning refers to deciding when the reconnaissance assets will be active. Scheduling refers to deciding what they will do when they are active. Planning is where do we put the sensing windows in time, and scheduling then is what operations do we put into the windows. This is a very large, very complicated scheduling problem. We're talking about thousands to tens of thousands to maybe even larger numbers of opportunities each day. And you can imagine how many combinatorially large possible schedules there are for doing that. And so we want to consider as many of these as we reasonably can and schedule the assets to do the best that they can. Often from an overall perspective, what we're trying to do is come up with come up with a way to maximize the time averaged intelligence value of the collected info, meaning on a long-term average basis. Now, in contingency situations, when the balloon has gone up, as the expression goes, often the objective changes. Instead, you're trying to get as much information you can about a specific hotspot or a specific situation. And then perhaps we don't worry about optimization at the global level. But in general, during so-called normal operations, what's going on is we're trying to do the best we can on average as long as we can, satisfy the largest number of customers that we can. There are some other concepts that are being studied, like the concept of dynamic retasking, which refers to using information that you have discovered to change the schedule of what you are about to do. And you can imagine this perturbs things pretty badly. These scheduling algorithms don't run real fast. And dynamic retasking can't be done really well on a short time horizon. Also, there are people who want to be able to schedule, to allow human intervention in this process in some ways. Perhaps someone comes up with a really high priority request and wants to put it in on a collect this or else basis. And so one of the questions is, how can you operate the system so as to allow that? You can imagine this has to be automatic. These things are doing 4 or 5 miles per second. They're going over lots of things all the time. The collection sequences are very complicated. There's no way a person could do this. And there's really no way a person can control it either. It's all automatic. Still, you want to be able to put human requests and other human considerations into the process if you can, sometimes. And what we do with our simulators is we study all of these things. We study the architectures of constellations, what assets should they contain, also concepts of operation, how should they be used. Typically, one of these is fixed and the other is variable. Given a constellation architecture, how should it be used? Or given a concept of operations, what architecture should be built to support it? And these are real questions. The agencies, especially the National Reconnaissance Office, spend very large amounts of money pursuing actual solutions to these. So these are real questions, and these are what the simulators get used to do. You can imagine that the complexity of scheduling a sequence of collection operations is, as one analyst put it, much worse than NP. Now, of course, there's no complexity class that's worse than NP. I'm kidding about that. But there's a whole lot of auxiliary computing that has to be done other than just reordering the operations in a schedule when you're considering an alternative. The reason for that is that how long it takes to do a sensor collection of a particular target is a function of when you do it. It's a function of geometry and lots of other things like that. And so if I move a particular collection operation, say, from the end of the schedule to the beginning, I have also changed how long it will take, probably. And that means I can't just treat these as fixed intervals of time and juggle them that way. Furthermore, from a geometric standpoint, I've got to maneuver the sensor from one target to another in between sensing operations. And how long that takes, of course, depends on how far it is from one to another, speaking in terms of angles. And I can't oversimplify that, nor can I ignore it. So every time I reorder a schedule, I may have to recompute it all. I may have to recompute all the imaging times and all the maneuvering times in the worst case. And in any case, I will often have to recompute a lot of that. So when we say it's much worse than NP, what we really mean is there's a lot of other computing that has to be done to support this, in addition to the NP complex scheduling problem itself. So it's difficult to get these, let's see, I guess we've covered all of this. It's difficult to get these scheduling algorithms to run in a timely manner. And that's one of the challenges. How can we come up with scheduling algorithms that do a good job, but are also fast enough to respond to real-time situations in a very dynamic problem environment? And another problem that comes into this is that vehicles are constrained with respect to, that's what I mean by WERT here, with respect to maneuvering. These things are large, some of them are flimsy, they've got noticeable moments of inertia, they have limited maneuvering energy, they can't just be yanked from looking at one target to looking at another. It takes time, and there are finite rates of angular velocity that they can achieve, acceleration that they can achieve, and also what we call jerk, which is the first-time derivative of acceleration. This is a term I was not familiar with before I started working in this area. Typically, when you're flying over an area that has a large number of targets, well, let's put it this way. The areas of most reconnaissance interest usually have a large number and a large density of targets. And so when a vehicle is passing over one of those, it will be making a lot of relatively short maneuvers from one to another target that are fairly close together. And every time it arrives at a target, it has to settle, it has to decelerate and stop, perform its imaging operation, accelerate again. So you can't, in general, use the approximation of constant angular velocity. You have to account for these accelerations and decelerations. The maneuvers are short enough, and we'll be looking at some maneuver profiles shortly. The maneuvers are short enough that you actually have to account for all of these values in computing how long they take. In other words, these dynamic constraints strongly influence the estimated maneuver times. I think we've adequately covered that. Here's a notional diagram of what this problem looks like. This dotted vector here, you see that? Yeah. That represents the trajectory of the satellite. It's actually bent, but we don't need that to illustrate the notion. And we call this R of t. R is the position vector of the satellite. T means it's a function of time. And we obtain this orbit somehow, typically by using a program that's known as an orbit propagator that computes vehicle positions and velocities as a function of time. Got a couple of target vectors here. And for simplicity, these are T1 and T2. These are a couple of target vectors. For simplicity, we'll assume that they are fixed in the coordinate system that we're using. These are not moving targets. They could be, but let's say these are not. And in reality, most of them aren't. There are things like cities and rivers and so forth. These two vectors here are line of sight vectors. The notion here is that at position 1, which was at time 1, we were looking at target 1. And when we reach position 2, at time 2, we will be looking at target 2. And the trick is, and the rotation, the angle that we will have rotated through is approximately this one, the one between that vector and the vector we'd have if we drag this one over here. The trick is that we don't know how long this maneuver is going to take, so we don't know how far we're going to fly, so we don't know where position 2 is. And that's what makes this an intrinsically iterative problem. How far we're going to fly while maneuvering depends on how far we're going to, how much of an angle we're going to maneuver through. And on the other hand, how much of an angle we're going to maneuver through depends on how far we're going to fly. That's why we're stuck with an iterative algorithm. An obvious iterative algorithm that does not work is the following. I can start here, and I can draw this target vector, which will not change because this position doesn't change, and we've assumed that the target's not moving. I can draw a bogus final line of sight vector here. This is just an initial approximation. I just use the starting position for the root of it, and I draw it to the second target. And that gives me an initial estimate of the angle I'm going to swivel through. And that gives me, if I have angle versus time characteristics, that gives me an initial estimate of the time it will take. That means I can estimate a position 2, draw this vector again, re-estimate this angle, re-estimate position 2, and keep going until this converges. What's wrong with that? Doesn't always converge. We never did find out why. We inherited an algorithm like this from let's just say, a major aerospace company that builds a lot of these things. And about once every 300 cases, it wouldn't converge. And that's not good enough for software, as I'm sure you know. This gives you an idea, just sort of a notional idea, what the coordinate systems look like. Problems like this usually use one or both of two coordinate systems. One is called Earth-centered fixed. The origin of the coordinate system is at the center of the Earth, and the coordinate system is assumed to rotate with the Earth, so that fixed targets on the Earth are fixed vectors in this coordinate system. The other coordinate system that often shows up in this is what's called Earth-centered inertial, meaning it's fixed to the center of the Earth, but it does not rotate with the Earth. And this is the most convenient coordinate system for describing satellite orbits, because the orbit propagator software typically gives you what's known as an ephemeris, that is, an approximation of the satellite orbit, in Earth-centered inertial coordinates. The gravitation doesn't know much about the rotation of the Earth. And of course, when you start computing these line-of-sight vectors and things, when you start talking about connectedness between the flying vehicle and the targets, you've got to be in one coordinate system. So the simplest way to do that is to deal with all the targets in Earth-centered fixed coordinates, and having generated the satellite orbit, rotate it into an Earth-centered fixed orbit, which looks like a broken slinky. I mean, you wouldn't want to see it. It looks like a deranged spring because of what the rotation does to this curve. You can imagine that. But that's the simplest way to do this. I can't draw one of those, but I wanted to explain to you this additional complication. Generally, you do this in Earth-centered fixed coordinates. And the reason I'm admitting that is this is not what the orbit looks like in Earth-centered fixed coordinates. It's a lot messier than this. But the mathematics all work. This is simply setting forth of the algorithm that I just suggested. I thought it was easier to explain it with the diagram. The blue part is the main loop. This is the part that repeats. These are the initialization steps, and then you simply repeat the blue steps here until finally the slew times and the slew angles converge. But this is the algorithm that wouldn't work for us. We tried this on another program I was working on. Never did figure out exactly why. For one thing, the angle versus time characteristic was estimated using the trace of a rotation matrix, and we did see some sign oscillations. We suspected that there were certain kinds of cases in which this was unstable. I was never able to figure out why or demonstrate that conclusively. And one of the reasons that this algorithm doesn't really work, or at least doesn't work as efficiently as it might, is that in effect it starts over from position 1 every time and tries to estimate the entire slew time in one jump. And if that fails, it goes back and tries to do the same thing again. It changes the magnitude of the jump, but it never does benefit from what it has learned, really, on each of these iterations. And that's why I wanted to see if we could adapt a route finder to solve this problem, which is what we're the question we're posing here, how can we do that? And the answer is, we can assume that each rotation takes place in a single plane. Imagine a vector rotating in a disk or something. That's kind of how you'd want to do it anyway from the standpoint of efficiency. A straight line or a straight rotation is sort of the shortest distance between two targets. We can derive angle versus time functions and their inverses, time versus angle functions, for these planar rotations from simple physics, equations we all learned in freshman physics. We can integrate the acceleration twice. If we know what the acceleration profile looks like, we can integrate it twice to produce a displacement versus time profile. This gives us a set of estimates of angle versus time characteristics. We also have another set of estimates. From the diagram that we looked at, you can see that we were able to estimate slew angles by looking at the vector geometry. Well, since these things both purport to estimate the same quantity, which is slew angle, why don't we just subtract one from the other? That ought to be 0. That gives us an equation of the form f of x equals 0. We can use a root finder to solve that. And to make a long story short, that works. And that's, in terms of general applicability, that's most of the value of this talk. You may be able to stabilize an unsatisfactory iterative problem by coming up with two functions that both estimate the same parameter and simply subtracting one from the other, and then using that as your update term in a root finder. In this case, that makes the Newton's method update expression look like this. We'll use the Greek letter theta to refer to the slew angle as based on vector analysis. That's the thing that we looked at in the diagram. We'll call xi of t the slew angle based on the planar rotation equations that we'll get from physics, and we'll generate successive approximations using Newton's method, which is, the next value of the independent variable is the previous value minus the ratio of the functions evaluated at that to their derivatives evaluated at that. Got a couple of spurious ampersands there. That's interesting. These ampersands don't belong there. I don't know how they got there. But anyway, this is just, those are supposed to be primes. That's theta prime and xi prime. Think of those ampersands as indicating derivatives. We've invented some new notation here. But, those of you who are familiar with Newton's method will recognize that this is just the conventional Newton's method update, f of x over f prime of x. It's just that in this case, f of x is one minus the other, the thing that we need to have go to 0. Okay, like I said, to make a long story short, this works. But let's look at how we go about coming up with those angle versus time characteristics for the planar rotations. We've assigned some notation to the maximum allowable value of angular velocity, how fast the thing can rotate, the maximum allowable value of angular acceleration, how fast it can accelerate in rotation, and a maximum allowable value of jerk. What these things come from in the real world is they come from limitations on what kind of energy for maneuvering the vehicle has, and also from structural considerations, like how fast can we push this thing without setting it to vibrating so badly that it would take too long to stabilize to allow us to take a picture. Some of these things are very large and spindly, and if you push them hard, they start wobbling, just yada yada yada, like a flimsy erector set. And if you push them too hard and get them ringing, as that's called, too energetically, it can take too long to stabilize or not stabilize, and you get a bad picture because the sensor was wobbling on this vibrating spacecraft. So that's the reason. That's where these dynamic limits come from. These are real. These are the things that limit our ability to maneuver from one thing to another. It turns out that there are multiple cases of what these maneuvers look like, and we'll look at these cases, and we'll also look at the reasons that separate them. There are also 5 subcases. But the thing that they primarily depend on is how far are we going. And I'll try to illustrate why that is. If I'm not going very far, I may not even, this is a curve that illustrates angular acceleration versus time. That's not actually what we're looking for. We're actually looking for angle versus time. That's the second integral of this curve. But it's easiest to illustrate how the limits apply if we use the acceleration curve, so that's what I've drawn. If I'm not going very far, I might not even reach the maximum allowable angular acceleration. We're assuming that the slope of this curve is maximum jerk. In other words, I'm jerking as hard as I dare, or as hard as I can. But in this case, because I'm not going very far, I simply have to stop accelerating, get busy decelerating, and then get busy settling back to zero, or I'll simply rotate too far. So this is what defines the first case. And in this case, the variable of integration is the entire duration of the maneuver. That's why it's shown in blue. You'll see the rest of the curves, we have both fixed and variable terms. That's one of the things that makes this a little tricky. It could be that I'll reach maximum acceleration, and then I'll have to stay at that value. I'm still accelerating, mind you, but the jerk has dropped to zero because it had to. We'd hit maximum allowable acceleration. Then at some point, I'm going to have to start slowing the acceleration, or I will exceed my maximum allowable angular velocity. That's what determines the point where this curve has to begin dropping. And then the second half of the curve looks the same. All these curves are symmetric. The assumption is that we're going to slow down the same way we accelerated and end up with zero everything just as we rotated as far as we needed to. So this is case 2. And in this case, the amount of time consumed by the parts of the curve that are shown in black, these amounts of time are constant. Therefore, their integrals are constant. Therefore, their contributions to how far we're rotating are constant. And the only variable is the blue parts of the curve, this one and this one. So that ends up being the part of the curve that we actually integrate in this regime. Or it could be that I'll reach maximum acceleration, and then I'll drop back to zero acceleration because I'm going to reach maximum angular velocity. And then I'll simply rotate at maximum angular velocity for any amount of time. Could be quite a while. And then when I've gone as far as I can and I've got to slow down, I run the reverse profile of this and I stop. I reach what they call the settled point right here. And in that case, this is the only part of the maneuver that's variable because both of these lobes are fixed. And again, their integrals and the angles that they represent are fixed. So we have to, when we're covering this case, we have to integrate only from this point to this, which is the variable. Okay, and then there's a second subcase. Well, there's a second major case with two subcases. It could be that my angular velocity limit is so low that I can't even reach my angular acceleration limit. If I do, I'll simply get going too fast. And in that case, we have two subcases, one of which looks like this. And again, these two triangles here are of fixed duration, and this is the only variable. And the other of which looks exactly like the first part of the other case. It's just the little zigzag. Again, the reason there is that I'm simply not going very far, so I can't even hit this acceleration. I can't hit this acceleration limit, nor have any rotation at maximum angular velocity. So we got 5 subcases. The slopes of these things are the jerk limit. It turns out that all of these break points that you see in every one of these maneuvers can be determined entirely in terms of these parameters alone. You can get them by simple algebra. So two integrations with respect to time produce angle versus time characteristics that are also in terms of these limits alone. And in fact, I've shown you what the expressions look like and also the time limits on the range of validity in terms of time for each of them. And it's not important to pay attention to the form of these equations except to notice a couple of things. One of them is that, as I said, all of the information is expressible in terms of these limits alone. And these guys are constants for any given problem. So you can derive these functions that you can generally reuse. The other thing is to notice that although this one is a cubic, it contains only these two terms. It doesn't have anything added to it. And all the rest of them are quadratic or are of degree 2 or less. So all of these functions are invertible. easily. The cubic inverts into a cube root. The quadratic formula can be used to solve the quadratics. And you can fairly easily produce time versus angle characteristics that are the inverse of these angle versus time characteristics. That turns out to be useful when we formulate the Newton's method solution. Again, the two things to notice are these expressions are entirely in terms of the three dynamic limit parameters, and they're all readily invertible. That's the only thing that's important about them. Estimating the slew angle from vector analysis is even easier. We simply form the unit vector forms of the line of sight vectors, take the dot product of these two unit vectors. That's the arc cosine of the slew angle. It's that simple. So now we have the estimates of the slew angle from rotational mechanics and estimates of the slew angle from vector analysis, and we can formulate the problem. And here is the simplified algorithm that implements that. We begin by estimating the two line of sight vectors, and we do that the same way as I suggested before. We use R1 in both of them because we don't have an estimate of R2. These are both approximate. And then we compute the unit vector versions of these two line of sight vectors, estimate the slew angle from the dot product of these two unit vectors, and we use our inverse function to estimate the inverse time versus angle function, which is why we're glad we have those, to estimate to come up with an initial estimate of the slew time. Then we simply iterate. We store that initial estimate. We estimate the final time from the initial estimate and the slew time. We estimate the final position of the vehicle from the final time. We can now calculate L2, the actual second line of sight vector. We can estimate, we have to compute the unit version of it too, because we need those unit vectors for this arc cosine thing, dot product here. That gives us an estimate of the slew angle from vector analysis. Now we use our angle versus time characteristics as appropriate. We got 5 of them. We got to pick the right ones. We use our angle versus time characteristic to come up with the other estimate of slew angle. And we simply update the estimate of the slew time from this Newton's method formulation. This is what it's supposed to look like, no ampersands this time. Guess I should have used derivative notation on the other chart. And we simply do this until it converges. How well does it work? I've never seen it take more than 4 iterations to converge. I've often seen it converge to 10 to the minus 15th on the 4th iteration. That's basically the limit of IEEE 754 double precision floating point accuracy. That's about the best you can do. It's implemented in about 100 lines of C++, and on a ordinary Pentium class PC, it'll run 80,000 slew time computations per second, which is what we need to put into a fast scheduler, because we're doing a computation for every maneuver in every schedule that we consider, and we're considering a combinatorically large combination of schedules. And so even though we have a fast slew model, an ISIS run, which may be considering a dozen satellites, 600,000 targets, and several days of operation, even so, an ISIS run requires hours and hours. And we've got lots of work to do to try to bring this down, because nobody's happy about these run times. They're happy about the simulation results. They're not happy about the run times. Sir?
Just to get some idea. Some average bogey value is
3, 4.
3 or 4 seconds.
It can't. There are actually satellites that'll only rotate at about 1 degree per second. These are really big, spindly ones with large, wonky antennas and things like that. I've heard that there are some that are dramatically slow. Just to complicate things, there are also satellites that are capable of steering their line of sight vector electronically, which is essentially instantaneous, at least within some narrow range. And so maybe to calculate the slew time, you have to figure out how far you can move it electronically, and if that's not enough, cover the rest with some sort of a mechanical maneuver like this and combine the two. In that case, the scheduling algorithm wants to try to arrange long sequences of targets that are so close together that electronic slewing can cover them all, and you avoid mechanical maneuvering entirely.
So crossing the U.S. thing,
Mm-hmm.
you could then conceivably snap.
It depends on the kinds of pictures you're taking, or the kind of things you're acquiring. Some of these are what they call area sensing, where you'll maybe take a picture of a city. And maybe you'll take it in small patches. And so you'll take lots of different ones and mosaic these together to form an area target patch. Sometimes you're just looking at a point. And the answer to the question varies widely according to what you're looking at and how they're distributed. If you're looking at cities, you might only take a few in a pass because you might spend all your time taking the little shots that you're going to paste together to make the city map. If you're looking at objects in the field, like trucks or something like that, and they're closely distributed, you might be able to do thousands in a single pass, even if you have to look at them individually, maneuver to look at them individually. And that's another one of the things that complicates designing the system to do this. The optimum approach to some of these situations is not necessarily the optimum approach to others. What are we doing here? Yeah, we're not sunk yet. Go ahead. Resolve the problem. What kind of a mechanic? Oh, okay. The satellites that I'm talking about are all unmanned, and the extent to which they can do things like that is quite limited. The extent to which any kind of work on them can be done. Maybe a what? Usually, I think when we were doing a simulation of this type, we usually would ignore things like that. We would assume that the thing is going to be working right, or that in other words, we will assume in advance that we know what its behavior will be, but there won't be any maintenance operations scheduled for during an operational period, something like that. They do require maintenance of various kinds. Things like they need time to recharge their batteries, they need time to cool off. If they're flying in the sun and imaging, they have plenty of electrical power from their solar panels, but they're getting hot because there's all the power that's coming out of the electronics, as well as the heat of the sun shining on the thing, it can heat things to 250 degrees in space. And usually the temperature inside one of these things is actually on the order of room temperature. The stuff is designed for some excursions, but there are limits to what it will take. I don't know if I've answered your question, but usually, and there is limited maintenance that's possible. Typically, the capability for that will have had to be built into the vehicle. Like if it's got to do a lens change, then you've got to rig it with an automatic lens changing procedure, or something like that. But those would be done during periods of inactivity, and we wouldn't account for them in the scheduling of periods of activity. Does that help?
Could you account for that in the schedule?
Mm-hmm.
Got some system in there to do that.
Mm-hmm.
Could you schedule that in as part of the?
Oh yes. In fact, you'd have to. Yes.
Part of the process is it takes 5 seconds to change one.
Mm-hmm. In that case, you've got to put that in as one of the considerations. And that's one of the things that makes it difficult to design a system like ISIS that's supposed to be a generic simulator that can be used to study a wide variety of problems of this type. Just about every time we're considering a constellation architecture or a concept of operations, it will have some aspect like that is resistant to generic simulation and has to be accounted for specifically. Let's see, in this case, this vehicle does thing X, and our generic simulator doesn't represent thing X, so we have to modify it so that it does, and now it's less generic. So you end up with lots of else-ifs, and over time, you end up with a million line. This is how we ended up with a million-line mess, basically. Does that help? That's.
Of course, it doesn't really probably make it easy to accommodate changing lenses while you're rotating and cut some of that time out using it in your maneuver time.
You do as much of that as you can. To the extent that you've got things you've got to do, you try to do them when they don't hurt you. And of course, there's constraints on this. One of the constraints, for example, is that there are vehicles that must never ever look at the sun. Here's some sort of a sensitive optical sensor that will be fricasseed the first time it looks at the sun. And maybe there's a cone angle constraint on it that says you must never look within even this many degrees of looking at the sun. And so you always, in planning these operations then, you have to make sure that you always know where the sun is and you're never asking the vehicle to look at it. Or always making sure that it can't. Or that you've got some emergency measure like the cover that slams shut in a hurry if you discover that you're starting to. Something like that. There's lots of ways for this to screw up. and that's one of the things that makes these expensive and sophisticated. Simulating the operation of a constellation has tricks, introduces considerations too that we have to think about. Some modes of imaging acquire data so rapidly that there's no possibility of storing it on board. You couldn't possibly have enough buffer. So the rule then becomes, this can only be done when you can either see a ground station and beam stuff down immediately, or you can see a relay satellite and he can see a ground station. And so this becomes part of what you're modeling. Part of the trouble is the relay satellites also service other constellations. So I got to keep track of what they're doing, and I've got to not assume that I can have a relay satellite when it's going to be busy with somebody else. And in fact, the people who actually do this stuff have very complicated systems for adjudicating that. And the rules are things like you can only put in one request, and you get what the relay scheduler gives you, and you don't get to ask again. Because they know that everybody would. And they say, no, that's not good enough. Put in another request. So the rule is, every time you only get to put in one, just to keep the constellations from fighting over the relays and things like that. And the more accurately you try to do this, the more of these considerations you have to take into account and put into the code. And of course, again, the more you do that, the less generic your simulator is becoming. I would call this an instance of the generality versus specificity trade-off that you've probably all run into, or at least you all will. Dr. Ray is nodding like he has seen that one before. More questions? Mm-hmm. Well, the old way was we didn't use it on such large problems. Mm-hmm. The upper limit of what we're hoping to do is like 100 vehicles. What is it? Something like 100 vehicles, 1 million targets in 100 days, or something like that. And we are nowhere close to being able to do that. We're nowhere, not even with the slickest parallel implementation that we can think of. And some parts of this are resistant to parallel implementation. There are constraints that apply to the entire constellation, like maybe the ground station can only talk to n satellites at a time, so only n satellites at a time can be working. That's not the kind of thing you can take into account in a parallel algorithm that schedules each one independently. Each process has to know something about what's happening in the other processes. So maybe you need sockets, maybe you need semaphores, you need some kind of a synchronization mechanism if you're going to do parallel processes. More questions? Sounds like fun? Here's why it's not fun. one of these things has 250,000 lines of Fortran in it.
It could be worse.
How? 500,000. Yeah. 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 Mm-hmm. The one of the simulators, Cosmos, you can all read it. Did everybody get a booklet? Got a bunch of booklets down here. If you didn't get a booklet, help yourself. This stuff is described on page 5. One of the simulators, Cosmos, is able to simulate in great detail the behavior of a communication network that is disseminating these results. And it can even simulate analysts working on analyzing them and messages being sent over networks. And you can put in network delays and stuff like that so that they can try to figure out what the real intelligence collection, dissemination, and analysis process would look like and what it would really take. This is what NGA wants to know, one of our customers. They're the folks that do that part of it. And they need to know how to organize their system so that it meets the timeliness requirements of getting all this stuff where it's supposed to go. And the Cosmos can even simulate message content and the reprogramming of some aspect of the problem according to someone receiving a particular message and making a decision based on what he reads in it. That's all part of the simulation. Want to know what's terrible? That's the stuff that's in Fortran. Imagine doing that in Fortran. I have no idea how they did it. I was here when they did that. It was 1990 or so. Go ahead.
How big is that? Like Cosmos, the tokens?
They're both about 1 million lines. ISIS and Cosmos both.
ISIS comprises C++?
No, it's mostly C.
Oh.
I'm trying to C++ify it. It at least compiles as C++. That is to say, it's all ANSI C. Cosmos, unfortunately, is mostly Kernighan and Ritchie C. And so to C++ify any piece of it, the first thing you have to do is turn the K and RC into ANSI C so that a C++ compiler will swallow it, and then go from there. This is highly desirable because C++ has the standard template library, which mechanizes lots of neat basic data handling functions. And those are good algorithms for the most part, better than the ones that were built in back at the dawn of civilization when this stuff was written. And so one of the updates that we're trying to implement to improve the performance is to C++ify a lot of the old K and RC code and replace the intrinsic algorithms with the STL because we think that works better. But it's challenging to do. C++ and Motif don't like each other very well in some ways. And Cosmos uses a Motif GUI. It's that old. So replacing the GUI with a newer GUI is another challenge. Coming up with Windows clients so that mere mortal users can use this is something that we're trying to do. They don't do Linux for the most part. Question? Mm-hmm. Well, what we're talking about here is a hard constraint that's system implemented. In other words, for example, maybe the ground station only has 4 channels. It really can only talk to 4 satellites at once. And it can be maybe any 4 of the satellites, but that becomes just to use an example. I mean, 4 is an arbitrary number that I grabbed out of the air. It can be perhaps any 4 of them, but it's a firm limit. You can't get 5. In other words, the ground station just won't do that. Yes. That's what the scheduling algorithm has to do, is try to figure out what's the best time to be doing everything, but in such a way that all of the constraints are always satisfied. Like at no time would I be trying to have 5 vehicles active, let's say, if the limit's 4. That's one of the things that complicates it. All the constraints have to apply all the time. Don't look at the sun means don't ever look at the sun. And that means consider this constraint all the time. That becomes quite a computational cost. And of course, we pull all the tricks that we possibly can. Like, by the way, if the sun's on the other side of the world right now, don't worry about it. But if the sun's close to the edge of the world, start worrying about it. And if the sun's known to be above the horizon, by all means worry about it. And sometimes we have multiple algorithms that we use depending on which of those cases we're in, where we try to find cheap cheats, if you will, to handle the marginal or the out of range cases. It's a lot like computer graphics, where you try to find easy tests that tell you what you don't have to do, and things like that. I did computer graphics at one point. I don't know if you've ever heard of a system called PowerScene. It was an early high-performance scene generating system that ran on an SGI Onyx. And we tried everything we could to get the performance of that up. I don't think we ever got it over 30 hertz. But the real problem wasn't that. It was that nobody could afford an Onyx. I mean, we had 4-star generals balking at the cost of Onyxes. Things like that. When the 4-star generals say, I don't think I can afford that, it means nobody can. An Onyx? At the time, this was, early 90s. By the way, that's the first thing I did when I left here. At the time, an Onyx was about $300,000. More than I had in my checking account. And the problem, of course, for the general is he has $300,000. That's not a problem. But what he's trying to figure out is, how can I supply these to my whole command? And that's what he can't afford. Yeah, exactly. Now, stuff that we used to have to use an Onyx to do, I think you can do with an NVIDIA board on pretty much any PC. As a matter of fact, I believe the folks who started NVIDIA were the advanced graphics group at SGI. They saw the writing on the wall. I said, gosh, you really only need a PC to do this if you have enough cleverness in your graphics subsystem. And they went off and created cheap high-performance graphics. And that whole business is gone. I don't know if SGI is even still around. Things move so fast. I left here in 92. I went to Washington in 93. I worked in the SGI world for the next 6 years. 3 years of high-performance graphics, 3 years of very high-performance database implementation on a room full of origins. And at the time, SGI was the berries. That was what you wanted for either of these kind of apps. And now it's 7 years later, and nobody even talks about them anymore. In how many fields do things come and go that quickly? I've been in Washington 13 years. This is my 7th job. The reason is there's no inertia in the software business. A project succeeds or fails very quickly. And either way, you're on to something else. And the odds are that the next interesting something else isn't where you are, unfortunately. That's one of the nice things about being in a place like Washington, where there's lots of things to do and lots of places to do them. If you're in the middle of nowhere when your interesting project ends, there may not be another one of any description. The odds are there won't be another interesting one. That's the disadvantage of the middle of nowhere. Now, this is sort of an unusual place. It's the middle of nowhere with lots of interesting things to do. More questions? Anybody want to throw anything? Go ahead.
Can you talk more about
I can talk a little bit about that. Let me mention that space-based reconnaissance, at least from the intelligence community standpoint, is what they call top secret and SCI. That is, sensitive compartmented information. And what we can't discuss are the specific capabilities of any of these systems. What the real ones will really do. There's 2 reasons that I can't do that. One of them is that it's classified, and this is an unclassified talk. The other one is, I don't know. I've been working on generic simulators, implementing the capability to do this in general, and not so much on simulating specific systems. But to answer your question as best I can, For a low Earth orbit satellite, a typical orbit is on the order of 90 minutes, and a typical amount of imaging time would be, let's say, 20. I'm just pulling a number out of the air, which is one of the reasons you don't get, a lot of use out of this, and why the optimizing the scheduling of it is important. There's also, there are limits on things like how many operational periods you can have per orbit. Perhaps my 20 minutes can be distributed over no more than 3 operational periods for some reason, that kind of thing. In other words, I can't have 10 2-minute imaging windows, even if I want them. There's got to be a certain amount of time that separates. These are the constraints I was talking about. Got to be a certain amount of time that separates every 2 operational periods. Maybe for cooling, maybe for battery recharging, maybe for de-spinning the maneuvering gyroscopes. These things are often maneuvered by gyroscopes, and those things accumulate angular velocity as they go. And there comes a time when you have to put the brake on the gyroscope and fire some rocket engines to counteract the torque and just de-spin the gyroscope. And that's one of the things that, because you don't want to leave these things spinning fast, they'll wear out their bearings. They've only got so many bearing cycles during their life. So from time to time you have to de-spin the bearings, and that means you've got to fire the engines, and that means you're using up fuel that you can't replace. That's one of the reasons that they like to use gyros, those that can be powered electrically, and you can replace that fuel with your solar panels. It used to be that they always did this with rocket engines. It used to be that satellites didn't last very long. That was one of the reasons. They would run out of fuel and become useless. Now they last a lot longer, but you still got to have rocket engines, even with gyroscopes. Got to have rocket engines to change orbits in any case. Can't do that with gyroscopes. You want to steer from one orbit to another, you've got to fire an engine. And they have to do that every so often because the orbits decay. The thing is, if it's low enough, the atmosphere is dragging on it. The Earth is not round. The Earth exerts a warped gravitational pull. The Sun and the Moon add their contribution, especially to orbits farther out. And you've got to fire the engines every so often to maintain the orbit. That's not one of the things we worry about. Go ahead. If you believe your orbit propagator, for a low Earth orbit, where the Sun and the Moon aren't so important, and if it's high enough that atmospheric drag also isn't important, orbit propagator will give you a pretty good orbit for a week or 2, maybe even a month. For a highly elliptical orbit or something like that, where the thing's going to be out away from the Earth and being influenced by the Moon, orbit propagator isn't too good. Those are the kinds of orbits that have to be maintained by firing the engines. And every time you do that, you have in effect established a new orbit, not the one that the propagator computed. That's an interesting question for just that reason. In a sense, our long-term simulations are unrealistic because we run the orbit propagator. It's the only thing we have to run, and it computes where the thing will be for the entire duration of the mission. But that's not accurate past a point. And the only thing that we can say about that is you really would fix the orbit. You would do what it takes. And so we claim that the simulation results are valid, even though we know that the orbital positions past a point are inaccurate. But to answer the question about scheduling, typically schedules are done out several days in advance. Maybe one day, maybe the thing will compute a sequence of one-day schedules. And how to manage those as things unfold is part of the problem too. There will be failures. For example, when you're taking pictures, radar can see through smoke and cloud, but electro-optical sensors can't. So you schedule a bunch of EO sensing, and you find out that half of it was wiped out by clouds or smoke. Now that's got to be, you don't find that out till you see the results either. Now that's got to be rescheduled. Those operations have been missed, and they've got to be put back in, usually on a high priority basis if they were important. And putting things in on a high priority basis often means running a shorter, less efficient or less effective version of the scheduling algorithm because you don't have time for the good one anymore. Maybe I got to get this schedule up there in 15 minutes. So I use a really crummy algorithm, and it gives me a really crummy schedule and says, here, and sticks its tongue out at me. All of these come out of overall effectiveness, all of these things. That's one of the reasons, currently we're being perturbed a lot by the customers. I want to be able to interfere with this process. And we have to ask them, how much are you willing to pay to do that? You will corrode the process. You can't convince a fighter pilot that he's not as good as a computer either. Not except by trying it and showing him the results. But at least in advance, it's impossible. I'm going to wiggle the stick, I'm going to fly this thing, and I'm going to do better than that darn machine. Right. You just have to let him, you have to hold your nose and let him try it. And say, here you are, sir, and you're 26% off optimal, or something like that. I'm going to go back and try it again. Well, after a while, they figure it out. But it's one of those things that you just have to go through. And again, all of these variations that hit you usually come out of the effectiveness of the overall results. In other words, it's like every other process you can think of. All the real-world effects tend toward making it worse. We really don't work on it. We aren't at that level of refinement. These are usually general questions about, we're talking about what we're going to do 15 years in the future, that kind of thing. It takes a long time to build and deploy these things, and they operate for a long time. So the analysis of future efforts is years out. And there's lots of uncertainties, like how good will the sensors be? Who knows how much progress will be made in many of the parameters that go into the simulation. One of the things that the customers want to know is, what are the parameters that make a difference? Where should I be investing my technology development dollars? If the sensors were twice as good and the results are the same, then I shouldn't be spending money on sensors. That kind of thing. So that's one of the things that they often want to know is, what are the parameters that make a difference in the way the thing works, given the architecture and the concept of operations that are being considered. But everybody knows that it's a rough approximation. We're talking about the future. And you can't believe the numbers. The thing that you're really looking for is, which direction do they go? Does making a particular change make things better or worse? But until you really have accurate values of a lot of the parameters, which is to say about the time you're going to launch this thing, you can't really do accurate simulation. Instead, they're just trying to get a handle on what's better and what's worse in terms of strategic decisions. $10 billion decisions, by and large. Or, how can we get it for only $9 billion? That kind of thing. That's one of the things that justifies this kind of effort. There's big money involved here. This is one of the few application areas I've worked in where an improvement is almost always worth making if you can see how to make it, just because of the amount of money and priority and importance that's placed on that. That's one of the things that makes it an interesting application area. There's lots of others in which there's many things that you can think of to do, but there's not enough money in the problem domain to justify it. That kind of thing. Or not enough something. Not enough urgency. Not enough people. More questions? We got some water. Still got some time. We can quit if you're ready. Any specifics? What now? I didn't hear that. Specific what? Sorry, I'm not hearing it. Any what? Statistics. Okay, thank you. I thought he was saying specifics. The room's a little muddy. What do we use statistics for? There are random numbers that are used to simulate certain kinds of things. one of the things that we use statistics for, and one of the things that we use randomization for, is simulating the behavior of large numbers of moving targets. Suppose you're going to do a simulation of something like a theater-level military campaign, where you're going to have, we do this with Cosmos, where you're going to have very large numbers of things moving, and you can't afford to program explicit instructions for moving every one of them. So you come up with some number of, some reasonably small number of movement protocols that are realistic, and you try to come up with some sort of a distribution of how many of these things would be behaving in each of those ways. And then you program it that way. You use random numbers to choose, and you use some sort of a random number distribution, a probability distribution, to assign behavior to the individual entities, and then you let them move. But you don't know what's going to happen because you've randomized and probabilized it. Does that help? We do lots of things like that, and that's a good question because it brings up another point, which is another branch of the generality versus specificity tree. We'd like to have the simulation be realistic, but we can't have it be agonizingly realistic because that takes too much specification. We can't tell every entity in this thing everything that it's got to do. So we use statistics to collectivize it to some extent, knowing that we're losing control. But in general, and sometimes the customer comes to us and says, I want to know what thing X is going to do in this scenario. And we have to tell him, we can't tell you. We've probabilized the behavior of thing X. And the random numbers may cause it to do this, but it might really do something else. It might be one of his buddies that does the thing you're asking about, that kind of thing. Often, we get this a lot from operational types. They want to know exactly what they're supposed to do or what their enemy is going to do, that kind of thing. And we have to tell them it's probabilistic. We're looking for overall effects, but you can't trust the results for any particular entity that isn't explicitly specified. And because approximations are involved, you can't even really trust those either. Again, what they're usually looking for is trends. What makes it better? Or what kind of decisions or what kind of changes make it better or worse? They want to know what the effect would be, but they've got to understand that we can't tell them exactly how much effect they would see necessarily. And statistics do come into it. There's a number of things that are randomized and probabilized, usually because of that. There's a bunch of them. They're going to have to behave differently, and we can't, we have no way of explicitly specifying that for all of them. It simply would take too much programming. Did a scenario not too long ago in which there's a very large number of small boats. Had to randomize the way these things move. The result was somewhat unrealistic because the movement was chaotic. They were buzzing around like gnats on the surface of the water. They wouldn't really do that. But it doesn't affect predicting the behavior of a reconnaissance system. You're really not concerned with how the thing is maneuvering, only with the fact that it's maneuvering and with the fact that it's moving, and will I see it? How much of the time? That kind of thing. So that's another thing that we have to worry about. What can we do with these simulation results? What do they tell the truth? And what would be too much to conclude from them? Anybody here do modeling and simulation in engineering or anything like that? Mm-hmm. That's a big issue, and it's one of the reasons why when you write these things up, you have to tell people what you did, because they need to know what they can extrapolate to and when they would be making things up by doing so from what you have done. People will always want to know, well, this isn't exactly my situation, but maybe I can come to some conclusions about my situation from what was done here. Ideally, your write-up will give them enough information to know if they can reliably make a leap like that. What kind of
things are only visible from the south. You've got a bunch of trees, you're not going to see what you're looking for except.
That all goes into it. Very good point. Sometimes a request will be made, I want a low sun angle because I want long shadows. Right. Somebody wants to know how tall a bunch of buildings are, and he's going to estimate that from the lengths of the shadows. So he asks you to shoot the buildings from overhead, but with a low sun angle. Sometimes he wants to look down into a valley, down into a ravine. So he says, give me this from overhead with a high sun angle. Sometimes he wants to know what the shape of a ridge is. So he says, give me this for the low viewing angle. But you know then, because you're looking through the atmosphere at a shallow angle, there's going to be a lot of atmospheric distortion. That kind of, he has to know that. Perhaps he has asked for a high-quality image with a low atmospheric angle, and you have to tell him, we can't do that. Take your pick. You can't get that image quality with that low a viewing angle. Too much, you're looking through too much air at too flat an angle. That kind of thing. These are all put in the collection requests, and they must all be accounted for in the scheduling. Again, you have to satisfy not only the operational constraints of the system, but also the constraints of the request itself. What does the guy want? That all goes into it. We compute what's known as an access interval for each target. An access interval is what is the interval of time during which I can see this target and all the constraints are satisfied. All the operational constraints and all the constraints built into the request. And it's those access intervals that the scheduler works with. It has to put the operation somewhere within the access interval, and then it knows that it's feasible. So these access intervals show up as a bunch of overlapping bars, but again, each operation has to be within its access interval. And sometimes you do things like sliding the operation forward or back in the interval to make something else work better. Maybe it shortens the maneuvering, increases the imaging time by 1 second, but shortens the maneuver by 2. That kind of thing. So you gain 1 second by doing that. And the capability to consider all these things has to be built into the schedule analyzer. There's a lot of geometry involved, a lot of numerical methods, a lot of different things, and even some AI, as you were asking. One of the things we try to do is adaptive algorithms. Teach the algorithm to watch how it's performing and change its own protocols. That kind of. We don't get to do as much of that as we'd like to. There's lots of good ideas that it's hard to find time to try.
Space memory requirements, that I've been refining it fairly.
Oh.
But system-wide,
There is a lot of memory utilization. I'm not sure I know why. That's one of the reasons that we're better off in Linux than in Windows. We found that Windows often doesn't handle large memory requirements as well as Linux does, not to mention being slower. On the other hand, Windows is a more familiar environment for many of the would-be users. And one of the things that we hope to do at some point is come up with a client-server architecture that involves Unix or Linux servers and Windows clients. And so we're going to have to work out all of those interface issues. And then we will have to distribute the design in such a way that the large memory parts of it are not in the Windows parts of it, unless we can convince ourselves that it can handle them. I'm not sure we know why it doesn't. We've never had, I don't know if it's the 2 gig, whether it's the 32-bit constraint or what. But, yeah. So far, that's what we've been telling ourselves, and we have not had time to resolve it, and we haven't had time to do the client-server architecture or implementation anyway, so we haven't worried too much about it yet. At this point, these things are entirely Linux. Are we over time yet? Yeah, we're over time. And anything else?
This is the last talk, so.
Oh, okay. So there's no such thing as overtime. I'll go as long as you want to. When the last person leaves, I'll know we're done. I did? Oh, that I studied it. Yes. Why did I do that? It was after I left the Air Force, and I decided I wanted to make myself independent of all the authorities I had learned not to trust in the shortest possible period of time. So I left the Air Force and I studied theology, and by the time I was 29, I didn't have to take their word for it. I hate to admit that. You know, I hate to admit that I spent 2 years studying theology in self-defense, but it's the truth. Anything else?
Thanks for everyone for coming.
Thanks indeed. I applaud you all. You came to a late talk. I didn't think anyone would.